Hello everyone! In this video we will continue to examine topic 5.4, magnetic effects of electric currents, and in particular continue to unpack magnetic fields. So, as introduced in the last video, a magnetic field can be preliminarily defined, we're going to refine this later, as a region of space in which magnetic dipoles experience a torque or turning force. And I want to sort of zoom in a little bit on why that happens, okay? So imagine your field at a particular point is pointed upwards, okay? And you stick your compass in any orientation into that field. What happens? Well, remember that the magnetic field arrows, right, align with the direction that a compass would turn. And so they are going to end up going from a sort of invisible north end to an invisible south end on the far side of the magnet. And we'll see that in a second, okay? And if this is sort of the south end and this is the north end, then the south side of your tiny little bar magnet, your compass, is going to feel a force in this direction, and the north side will feel a force in this direction of approximately equal value, very close to equal in this approximation. And as a result, your compass will turn to align with the field. Okay, that's what defines the magnetic field. The magnetic field is the purple thing that causes this to happen. All right, it is represented, although it is a vector field, with magnetic field lines, just like electric field lines are used to represent electric field. Okay, again, the way in which field lines can be a little bit deceiving is that they are sort of smooth and connected and they curve. Remember that the field itself, right, is closer to this with tiny discrete arrows, vector arrows, with a magnitude and a direction at every single point in space. But this is a good way of getting a sense of the overall structure of the field. As with electric field, the closer the field lines are together, the stronger the field, and the direction is indicated for the field line as a vector tangent to that point on the field line itself. Notice that the way that this works then is that the magnetic field points from the north end, to the south end on the outside of the magnet. Okay, I'm going to emphasize that a couple of times. So the magnetic field lines point from north to south on the outside of the magnet. This is the magnetic field pattern of a simple bar magnet or magnetic dipole, and it's something you should be able to freehand draw. Okay, so this is something to know and be familiar with, and be able to freehand draw, with the arrows indicating the direction as well. Note that, unlike electric field, I'm going to be pretty picky about this, and we'll talk about why in just one second, but unlike the electric field, you should not have field lines that sort of point out and disappear into space, okay? So this is something we do with electric field, but you never want to do that when representing the magnetic field. Sometimes you will see representations that do that, but I'm going to strongly discourage you from it. Why? Well, consider for a second breaking a magnet in half. What do you get when you break a magnet in half, right? You might think that you get sort of a North Pole chunk and a South Pole chunk, but as it turns out, that's not what you actually get if you've ever used a magnet or ever tried this out. What happens is that you just get two smaller magnets. So each of the chunks of the magnetic material are now themselves a magnetic dipole. They have a north and a south pole, and a north and a south pole from splitting that in half. And that is due to sort of a fundamental physical principle that can be characterized in a couple of different ways. The first is that there are just no magnetic monopoles. This is sort of a restatement of this particular fact, is that you cannot have a chunk of North Pole just hanging out. All right, they don't exist. It's not that they're somehow conceptually impossible. They just do not, in fact, exist. Okay, and actually, sort of studying the imitation of a magnetic monopole and like maybe they exist. This is actually sort of an open, active field of research, but generally accepted is the principle that empirically there are no magnetic monopoles, and this is directly connected. Okay. To the following principle. which is that all magnetic field lines are actually completely closed loops. And what is going on inside the magnet is that the field lines are closing themselves off as closed loops. This is in part why I don't want you drawing magnetic field lines that sort of trail off into space. Electric field actually does sort of trail off into space, but all magnetic field lines come in the form of completely closed loops. Now, how does that look like inside the magnet? Well, that's why things are a little bit tricky here, because if you close off the magnetic field inside the magnet, all right, so you represent the magnetic field as sort of going through the magnet like this, you'll see that inside the magnetic field lines are pointing from south to north, which is opposite of the direction they point outside the magnet. So recommendation, strong recommendation, memorize this particular fact and use it to figure out this particular fact. That is, memorize that the magnetic field points from north to south outside the magnet, and then you can close the loops off if necessary. But the fundamental physical principle is that actually the fundamental structure of the magnetic field are these closed loops. They have to close. Now, what does this mean? Well, think about sort of what is going on here. It means that basically this north-south pole structure isn't a really good understanding, or won't give you a really good understanding of what is fundamentally physically going on. And in fact, as we learn more about magnetism, I'm going to drop discussion of north and south poles altogether. Why? Because the reason a north and south pole is what it is because the field lines loop all the way through. And they sort of treat them like poles, okay? They're treated like poles because they sort of act like positive and negative charges. But fundamentally, there's no real thing that corresponds to the North Pole over here. There's no physical representation of that. The fundamental physical reality is actually closer to this magnetic field line representation. And we're going to see more about that. I'm going to explain more in detail what I mean. But the point is that the force per unit X charge for defining the magnetic field no longer works. So there's a really important sense in which magnetic field is going to borrow some concepts from electric field and gravitational field. But electric field and gravitational field are shockingly similar structures. They really have dramatic similarities in the way that they work, how they operate through the world. The only major differences being the difference between the constant K and capital G, the gravitational constant, and the fact that there are two species of charge and only one species of mass. So those are major differences. But other than that, they operate in shockingly similar ways. An electric dipole and two attractive masses are going to produce very similar structures. And both of them rely on this force per unit blank construction for the definition of the field, either the electric force per unit charge or the gravitational force per unit mass. But if there are no magnetic monopoles, then there's no pole to put right here. And so this construction of our idea of magnetic field doesn't work. If there's no such thing as a bare pole, then this kind of definition isn't even possible. All right, and so we're going to need to investigate more about how the magnetic field works in order to get a better sense of how to carefully define it. We will define it carefully eventually, but we need a little more background on how it's going to work. And the other major point is that this fundamental structure of magnetism and magnetic field is a closed field loop, not a bare pole.